Alright, silly people, here's the situation. This problem is kind of just an exploration of the idea of cohesive energy, which is like, why doesn't any metal made of atoms and electrons just like fall apart immediately whenever the electrons have energy? And it's because the energy of the total has to be less than the energy of the each individual atom in the thing, right? Which is interesting. So the first part of this problem is to estimate the energy of the n isolated atoms that is in that sort of framework by treating each one as an electron in the ground state of an infinite square well. Well, the energy of an electron in the ground state of the infinite square well, E1, is pi squared h bar squared over 2ma squared, where m is the mass of the electron and a is the width of the well, right? If the system is just n those, then the total, individual atom energy is n times that. So it's n pi squared h bar squared over 2ma squared, and that's that. Uh, this is to be compared to the energy if all of the electrons were treated as just a big infinite square well, and they're all in the same one. Um, so the next part of the problem is to find that energy as well. So this is going to be, I'm going to call it composite energy, or I guess total energy is what I'll just call it. Uh, and so here's the thing. There's a thing called the Pauli exclusion principle, which is saying that if you have a bunch of electrons in the same system, then they have to all be in different states. So all of these individual electrons right now have energy pi squared h bar squared over 2m, and then the width of the well now is n times a squared. But then each one contributes a different little n squared. So you can add them all up together to get a sum from n equals 1 to n of n squared for the lowest possible version of that, right? So this sum here actually has a closed form. It's a Maclaurin series, and also the squared is on the outside of the parentheses in this expression up here. So this is n squared, a squared. This is a Maclaurin series of the form n times n plus 1 times 2n plus 1 all over 6, which means you can write it as just distributing the 1 over n squared through the whole thing. N plus 1 times 2n plus 1 all over 6n. Kind of cool. Part C is the difference between these two energies. So remember we said that the the total energy has to be less than the energy of all the individual atoms. So we're gonna do E cohesive is the E individual minus E total. So it's the difference between the two. So, but they both actually have 2ma squared attached to them, right? It's just that for the individual energies, it was just n times that. So n times this plus or minus here, n plus 1, 2n plus 1 over 6n. One specifically asks for the cohesive energy per atom, so this is what it's actually looking for is the cohesive energy divided by n. So we've got 2ma squared. This is 1 minus n plus 1, 2n plus 1 all over 6n squared. And that'd be a fine form to leave it in, except the problem then asks what is the cohesive energy in the limit of large n. And this is interesting now because we can, for the limit of this, where we want to put this in a form on the right-hand side where we can use L'Hopital's rule. So we need a fraction of stuff which depends on n divided by stuff which depends on n. So let's just make this whole thing under the denominator of 6n squared. So you'll get a 6n squared coming from this term. And then let's just try and distribute this fraction out. So you're going to get 2n squared. 2n plus 1n makes 3n, and then minus 1. Which means, simplifying a little bit more, 6n minus 2n squared is going to be 4n squared, and this is going to be minus 3n minus 1. And it's all divided by 6n squared. Now the limit of this, as n goes to infinity now, is going to be, and let me write the left-hand side again just to be nice, is going to be the limit as n goes to infinity of this stuff on the right-hand side. So again, I already alluded to it, we're going to use the L'Hopital's rule to make this limit something that we can work with. So taking the derivative of the top and the bottom with respect to n, we're going to get 8n minus 3 over 12n, and that's still infinity over infinity, so we're going to have to take the second derivative of the top and bottom with respect to n, which is going to give you 8 over 12, and 8 over 12 is a reducible fraction. It's going to go like if you divide the top and bottom by 4, you get 2 over 3. So this 2 cancels out this 2. And so the limit of the cohesive energy as n becomes very large is pi squared h bar squared over 3ma squared. Fun. Finally, the typical atomic separation in a few angstrom. So like A is 4 angstrom. What is the numerical value of the cohesive energy per atom in this model? So part D is just asking you to plug numbers in now. So E sub c over n for very large n, using this formula, is going to go like pi squared. Then you can use the like the SI unit versions of each of these, or the the EV versions of them. I'm just going to use the SI ones. M goes like, it's the mass of the electron, so it's 9.11 times 10 to the minus 31. And A is 4 times 10 to the minus 10 right now. And then if you divide the whole thing by 1.6 times 10 to the minus 19, you can get your answer back into electron volts. Plug this into your calculator, you'll get something like 1.56 electron volts, roughly. It says that the measured values in this for this are in the range of 2 to 4 electron volts, but we got something less. But you shouldn't be worried about that, because we cleverly ignored spin when we were doing the Pauli exclusion principle bit. So if we included that, we'd probably get something a lot better, but we didn't. So there you go.